Hey Hannah, do you hear me?
Yes, I can hear you.
Okay. All right. Uh, it's about 8 o'clock, so let's just start our session. So, is this something you want to discuss today?
Oh yeah. So I have a quiz coming up on the first unit of E&M, and
Mm-hmm.
my teacher assigns us homework like every day, and I think for a couple of days I've just caught up on the homework. And there's some questions I have. I sent you a document with all the questions and also her answers as well. And there's like for each problem, I just have like a quick like little question for them, and I just added them onto the doc. So I was wondering if it's possible to go over that.
When did you get the assignment and you know um, the schedule from your teacher?
Oh, she updates it like every night. Like she gives us
Every
homework.
night?
Yeah, we get homework. Yeah.
Okay. The one you want to discuss tonight was out today or yesterday or day before yesterday or when did, did it
It was
come
just
out?
it was the homework from this week. Yeah.
This week? Do you know the exact what date was that homework was?
I'm not quite sure. I just went back in my notes because usually when I do the homework, I circle the problems that I need like help with. And then I just went back today and I looked back at what I had trouble with.
So I need at least one day to help you and or just overview that, or take a look at the problems. Okay, so give me just a one day, at least one day notice ahead of time. If you got I mean, the best case is if you got the any problems or homework problems from your school, just ping me right away.
Okay.
Then, or just send me you can email me um, homework problems or quizzes or um, you know, anything from your school right away. That will help me to actually give you the better feedback. Okay. So if I get your just homework and just tell me just a few hours before our session, I mean, I can still take a look, but I have my schedule.
Mm.
So it's really hard to actually take a look at your, input right away. So if you give me the heads up, maybe like a day notice, then it help, give me the more time to more carefully review the problems that gets you the better feedback. So I think I already mentioned before. So if you get homework or quizzes, anything from your school, um, the sooner the better. So if you just uh, give me like maybe 1 or 2 days heads up, then I'll just take a look and then I can discuss that in our session.
Okay, I think the only reason why I wanted to cover it is because some of the questions I have are very like niche and it's kind of hard to explain. That's why I thought it
Mhm.
would be easier to just like verbally explain it than like type it out.
I
Um,
mean, yeah, I mean, I understand. I mean, it doesn't matter. I mean, it's just um, you, if you, especially regarding the problems on your um, textbook, then I can easily find the problems. I take a look at myself. So if your homework problem from your textbook, then just all you need just give me a problem numbers, and you can just say I'll just I take our teacher my teacher actually homework out of this book from this problem number to that problem numbers, and I'm not sure I understood correctly how the problem was solved, and my question is this and that, then I'll check and then just get you the right answer and then correct solution on that problems. So, there's like some other schedule I have before your session. So, if you just email me a few hours before, then there's absolutely no time to actually just, quickly take a look at your, problems. I want you to just give a proper, feedback and with the right solution and answers. So if you give me like ahead of time. And just my rule, that's my general rule, is that all the students, they normally give me the heads up at least day before my session. But still, you can send me something that day, but it's not guaranteed I can, get you the proper feedback on time. So it'd be nice if you can just give me the like your question and whatever you want to discuss, right away when you actually get something from your school. Okay.
Okay.
So can you maybe go over the problems you are in trouble with and you want to just actually discuss today? And then I can just take a look at it and we can discuss what I can do to help you. And as I said, if there's something I cannot answer, then I can take a look at and give you better feedback during the week that, during week before next session or even in next session, okay? In the next week.
I think really quickly, the document that I sent you, it has like
Yeah.
it has the link to the textbook, so it like, and I wrote down the page numbers and the question. The
Um, okay, then why don't you share your screen and then maybe just you can directly ask me the question. I can answer right away then.
it says host disabled participant screen sharing.
You'll not be able to share your screen?
No, you have to go to the like host like permissions, and then you need to
Okay,
let.
hold on a second then. Let me I think guest can also share their screen too. Okay.
um
Let me check more option. I don't see any additional option in Zoom. So how about I can share screen, my screen, and then I can just open your email and you can explain your question with your email, the link, whatever you send me that, right? So that I can maybe directly answer on that. So let me open your email. Hold it. Okay, right there. The link to the question. Okay. So you send me the link of PowerPoint, I mean the Word file, right?
It should be called questions E&M. It should be like a Word doc. Yeah.
Okay. Let me share my screen. Is that right?
Oh yeah.
Okay. Why don't you start from first one?
Okay. So that one is it's
Oh,
like
okay.
I have the physical textbook. Let me look at it really quickly.
So this is page 651 of the holiday, the textbook.
Yeah, the textbook link is right there.
Okay, let me 651,
Yes, number
number
one.
one.
Yeah,
Okay.
I think I understood my teacher's explanation,
Mhm.
because she basically said that electric fields, when they're more dense, that's gonna be like that's gonna lead to a greater linear momentum of the proton,
Mhm.
which
Mhm.
which I understand, but
Mhm.
the linear momentum formula is
Mhm.
P is equal to m delta V. So delta V is also equal to acceleration is also equal to delta V over delta T. So delta V is equal to acceleration times time. That's kind of what I wrote in the document.
This
Um,
one?
yeah, so your momentum is equal to your acceleration times
Mhm.
time, essentially.
Mhm.
So what I wrote is momentum is basically like if you take that m times delta v and your
Mhm.
basic concept of acceleration is equal to velocity over time, you
Mhm.
can solve for velocity. So p is equal to force times delta t.
Mhm.
But time you don't really need to regard in this
Yeah,
question, so you
yeah.
can focus on force.
Mhm.
And we know that force is equal to the kp times p over r squared, like the electric,
What is P here? The momentum?
or k q. That's my bad.
KQ, right?
Yeah, times q over r squared. So I think my question is like the q oh yeah, that's supposed to be equal sign.
Mhm.
Q has a like negative or a positive charge. So
Mhm.
I thought in these three scenarios, does it matter if like for A it's positive and B is positive negative? Like does that have any
No,
effect?
no, that's the force, static, electrostatic force itself, um, is only depend on the quantity of charge. F equals QE, and the E is electric field, right? And when you, so here you said you put that this equation, and that F, you said this actually equals, right? And then this is force definition of electrostatic force out of charge, right?
Mhm.
And if you add that, and doesn't factor the magnitude of momentum. How does it affect the sign of the particle charge? How that affected this momentum has, this is delta t, has the time term has nothing to do with the momentum in this definition, right? As you write. And then F equals, even if like minus plus sign, then there's acceleration right there. Delta P, the four. I mean, I don't see that any connection between the sign of the charge with the, how does it, is it connect, how is it connected out of these formulas?
Yeah, because momentum is
Yeah.
based off of force, and
Oh,
force takes the sign of the charge into consideration. So I thought
uh-huh.
that because they're connected, that momentum would also take the sign of the charges into consideration as well.
Yeah, I
Because
mean, yeah. Now you
or
can test it. You can plug like a minus sign and plus sign into the this electrostatic force, Coulomb's force, right? And then plug back into the momentum equation. How that change that the momentum itself. I mean,
oh,
that direction is changed, obviously. That direction of force is changed, but the magnitude of the force is not, has nothing to do with the sign of the charge.
mm, um,
Because, right, that field, as you said, now in the condition is now you have proton positive charge in the position A, right? And you're looking at the electrostatic force at the position B under the electric field existing in the space. So the field itself only depends on the uh, density within the given space of the R. So if you have higher the field, more field within the space, then charge experience more force, which makes that the momentum is higher. But the direction is only determined by, I mean, the charge, the sign of charge also only determine the direction of momentum. But the magnitude itself is only depend on the distance from the observation point or quantity of charge. So
yeah.
now,
Or I think like I was talking about like instead of like I know the magnitude would stay the same,
mhm,
but if the instead for like scenario A, if it was,
mhm.
I think right now it's proton and proton, I'm pretty sure.
Proton, right? Positive charge,
So it
right?
would kind of like go away from each other, I think. But if it was like right now, like the proton A and proton
Mhm.
B, and the electric force would repel away from each other, I think. But if it's positive negative, wouldn't the force be doubled because it's going the same way?
Let me read this problem more carefully. And the rearrangement, like field and in the arrangement, proton is released from rest at point A. There's only one particle in this problem. The proton A, and proton is actually just at rest, point A, and then just accelerate toward the point B by electric field.
Oh,
So,
B is just a point on the field. It's with
right.
like another particle.
There's no particle, just one proton accelerated by the electric field. So there's no, repelling force or attracting force. Under this electric field, if you have plus charge or minus charge, they should experience acceleration by Coulomb's force. F equals QE. Here, the E is electric field, and the Q is point charge inside in the electric field. So this is the typical problem of how charged particle accelerate in the electric field. Within that circumstance, the amount of force only depend on the density of electric field. You see that difference? If you have
Yeah.
two charged particles, obviously they produce. So this is kind of like you may be probably mixed up the two different scenario. Let me just change presentation mode. So where's my PowerPoint slide? Okay, right there. Oops. Hold on a second. Oh yeah, right there. Okay. Let me open up the. So you don't want to just mix up the two different scenarios. Right now, this problem is assuming already there's something field from somewhere. So there's no secondary charge existing. Maybe that electric field produced by the charged particle or electrode somewhere in the far distance. But the basic assumption in this problem, the field itself already produced by some sort of charges. What? Hold on. There's something going on here. Let me. Oops. Okay. So there's some sort of field here. Oh, what is that? Okay, here, here, here. And this space already filled with the electric field. We don't have to, we don't have to know about where that electric field comes from. The problem itself only pre-assume, assume there's electric field existing. Now you add the one test particle, could be the proton or could be the electron, any type of charged particle, so merge into this electric field. That electric field, that charge point charge will experience Coulomb's force. F equals QE. So here, doesn't matter what charge, positive charge, oh, I don't know what, could be a positive charge or negative charge. Their force, they're same. Direction might be different. If it's a plus charge, maybe right hand side, or if it's minus charge, probably just experience the force left hand side. But their magnitude itself only depend on the charge and the electric field. So this problem, let me go back to the problem. Is here, you just leave the proton at point A, and this whole space already filled with the electric field, but with a different gradient or different distribution. And now you have proton as a point test charge, and that proton starts being accelerated by the electric field and moving from point A to B, A to B, A to B. But they should experience different amount of field, different amount of force out of the Coulomb's force. F equals QE. Okay.
Okay, so you don't so I guess like in my teacher's explanation, it was like you start off with P equals mv, and then the velocity, eventually a linear momentum is equal to P times the force times time. And because the force is dependent, the force changes based on the electric field. So the
Mhm.
denser the electric field
Mhm.
is,
Mhm.
the more force it's going to
Yes,
experience.
yes, yes, yes,
Oh,
yes,
more linear momentum, and
yes,
it's not
yes,
dependent on the sign at all.
yes, because you have more density of the electric field existing in the space that produce more force, then that bring up the more acceleration, which increase the velocity too. So as you know, the momentum is the force times time variation, right? So if you have more force, then obviously you create more linear momentum. So if you just connect the puzzle all together from the Coulomb's force all the way to the linear momentum, only matter is how much acceleration possibly created by the amount of electric field onto that pointed charge. So in order to make a more field or more force, you got to just create the more density of field inside of space. So for example, I think I should just change. I don't know why this PowerPoint slides work weirdly. Okay, right now, for example, you learned the two plate problem before, right? That was the last example we actually discussed last session. So let's just assume you have two plate, okay? So obviously two plate create the electric field in parallel. So that one positive, electrode, the plate produce the electric field outward, and the negatively charged plate create the electric field inward. So that basically electric field produced from the plus charge to negative charge. Now, let's assume that you add the proton inside of this two plate. Then obviously this one should be accelerated by the electric field. But this problem itself just ignored outside of this box and then just assume, oh, there's some sort of electric field already existing in this space. And what's going to happen if you add a proton inside of this area? Okay. So in that case, force itself only matter of how much electric field passing through this area of interest. Okay. There's no plus plus or minus minus or plus minus kind of relationship need to be considered in this problem because only matter is how much electric field you have in this given space. If you increase the charges, if you just biased with the higher voltage there, then it produces more charges on the surface that produce more electric field density. Then this box filled with more field, then this proton will experience more force out of this higher density of electric field. Okay? The same thing, if you just produce a different gradient, then proton will experience less density area to the higher density area to the lower density of electric field area. So that field itself will experience less amount of force along this direction. So they're gonna like gradually just slow down. So how much amount of force produced in given space onto the point charge is pretty much depend on the density of electric field based on the Coulomb's law. Okay.
But in the problem it stated that I remember it said like rank based on the angular momentum, like not the magnitude, but just like the angular momentum itself. If you didn't have a proton and you had like an electron, the force would be going the opposite direction, making it negative, making the linear momentum negative as well. So does that mean, since it doesn't ask to rank on magnitude, but instead it just says just rank based on angular momentum, if you have a electron instead of a proton, that would have the least angular momentum, right?
Then that has same amount of angular momentum, but in the opposite direction.
So because it doesn't say magnitude and it just says rank, because it's in the opposite direction, the angular or linear momentum would be negative.
Does the problem ask you, you need to rank in certain direction or A to B?
It just says like rank based on like what's the greatest angular momentum. And because angular momentum can be negative or positive, if you have a scenario where it's not a proton, but instead it's
Well,
electron.
here, let me change then change that actually condition of problem. Then will electron will not be accelerated from point A to the B. It's gonna accelerate point A to the left-hand side because it's negative charge. So direction is different, but there, so here two different conditions you actually apply to the modify this problem with. First, you change that sign of charge, right? From positive to the negative, right? That's first modification. Second, the mass is changed too, from proton to the electron. So FII, the proton is 2,000 times heavier than the electron. So that will completely change the momentum. So just ignore, let's just ignore that the mass part, okay? So if you leave that the electron at point A, same spot where the actually proton originally just located in the initial, initial time, then this electron will not be accelerated to this direction. It will accelerate the opposite direction. But if you assume that the proton and electron have same mass, then they should have same momentum, but in the opposite direction. The sign of the charge determine the direction of the acceleration, not magnitude of acceleration itself, and magnitude of momentum too. So if you
Yeah,
have
so
like a field here, then you have plus charge and minus charge, and plus charge accelerate this way, then minus charge should be accelerate the other way.
yeah, so if the question asks like if the like rank the different scenarios from the greatest linear momentum to the least linear momentum,
Mhm.
would you say the proton would have the greatest because it's going to the right, and then you
Mhm.
would say the electron has the least because it's going in the opposite direction, so the linear momentum will be negative?
I mean, basically then you have to change the question too. And you got to leave that electron at point B, not point A, because that's going to accelerate to the left-hand side, not right-hand side. So it's electron, if you leave the electron on point A, it's never going to reach the point B. Do you understand? So if you,
Yeah, I
there's 2 points, point A and B, right? The proton leave that, and the proton is accelerated by the electric field, this direction. But if you leave the electron there, it's not going to just going to this direction, it's going to the other direction. So how can you actually, and then you have to maybe, in order to equally, fairly actually compare two different scenarios, then you have to just change the question. Then you leave that electron at point B, then it will accelerate this direction. But with maybe like if you electron and the proton have same mass, then they should have amount of linear momentum to the right-hand side. It should be same as the one to the left-hand side. But their direction is just different, the opposite.
Okay, so they have the same magnitude of the acceleration, but it's just in opposite
Yeah,
direction.
opposite, as long as they have same mass.
Okay, okay, that
But
makes sense.
their mass is, as I said, 2,000 times different. So the proton and the electron will obviously have different linear momentum due to their difference of the mass.
Yeah,
Okay, does it make sense?
yeah.
Okay, okay. So again, back to this original question, there's no plus and minus charge relevant or minus plus charge relevant. Only matter of the which direction of the charge actually accelerated with respect to their sign of the charge. Okay. All right. And the number two, is it number two, right? 651, number
Yeah.
four. Okay, and let's take a look at 651. Oh, okay, now great. 651, number 4, right? Okay, so here,
Yes.
this one, is it right? Is that right? Yeah, 651, number 4.
Oh,
So,
wait.
is it right?
Oh, I think the next page. I think I wrote the page number wrong. If you go to the 651 and it's should be like 652, I think.
This is one, number 4. You know, like 652, number 4?
Yeah, there should be another number 4 coming up soon. And that should be it. Maybe one more page. Yeah,
This one?
around here. There should be a
Okay.
4.
This one, right?
Two charged particles are
That's the
attached.
x-axis. Particle one,
Number 4.
number 4. This one, right?
Yes, that one. Yeah.
Two charged particle and attached on x-axis. Particle 1 of charge -2 and there. And particle 2 of charge plus and C is position towards 1 midway between the particle. What is that electric field in unit vector notation? So, what is your question then?
I think most of my confusion when it comes to the basics of electrostatics
Mm-hmm.
is electric fields is I don't understand like the charges, I think.
Mm-hmm.
So my teacher, like I understood her work and everything.
Mm-hmm.
It's just it's KQ of the first one over D squared plus KQ over D squared or K cubed 2 over D squared and you just add
Mm-hmm.
them together.
Mm-hmm.
But my problem comes when it's with the charges because one is negative and one is
Mm-hmm.
positive.
Mm-hmm.
Um, so my teacher said the total electric force is
Mm-hmm.
going to the left, but I
Mm-hmm.
thought it would be going to the right. Because one is negative and one is
Mm-hmm.
positive, so it
Mm-hmm.
would be attracting to the positive, and the other
Mm-hmm.
one would be like going to the right as well, I guess. So I thought the total net electric force would be going to the right. And when you solve the equation, I thought it would just be the Q1 is negative. So in the
Mm-hmm.
equation, there's a negative sign
Mm-hmm.
and Q2 is positive. So you would put a positive sign in the for the
Oh, you know, like it just you got to be careful. You don't want to mix up the like sign of charge with the direction of vector. Okay, so you want to just stay with the vector notations, or you can just ignore the vector or just use the sign of the charge. Okay, so the best way, easiest way, simplest way, and just draw the arrow out of the charges in observation point, and it help you to assign the forces, and then just add them all into the vectorial space. Which mean by that, now let's take a look at the this condition, right? Number 4. Do you understand what I said?
um kind of. I don't get the difference between vectors and like the direction of vectors, but
So
also the
what if you just consider the direction of vector and also just add the sign of the charge and your double, you know, multiplication. So that produced the wrong sign of the sigma summation of the individual forces. So either you have to just add the vectors of forces in the observation point, or you just use that the same direction of the force and then just apply the sign of charges. Either one is fine, but you got to be very careful. You don't want to mix them up, then you got to just end up with the wrong result. So let's see. Now let's take a look at this one. Two charges are attached to the x-axis. And where's my okay, oh, right there. So if I change the presentation mode, I won't be able to actually just see this problem. Can you maybe just help me to actually, so now you have a 1 point, some in x one dimension, right? and the other one is somewhere here. Do you have that problem in your computer?
Yes, give
This
me
is
one.
Q1 and this is Q2, right?
Yes, 650.
And they're physically separated. What's this? Let me just check that. Oh, I don't worry about it. I'll maybe just quickly take a look. I can maybe still use my
Okay, I have the distances.
okay, so right here, this oops, okay, there's oop, oh, I don't like it. They respond much slower. Okay, I'm gonna move up. Okay, so the 1 point charge is 1 point, and the other one is Q1 and Q2. What's the distance between two?
So it says that particle 1 is at position x is equal to 6 centimeters,
6 centimeter
and
and
then Q2 is 21 centimeters.
21 centimeter. And then Q1, what's the charge of the Q1?
-2 times 10 to the power of -7.
7 coulomb, right? And this
Yes,
one is what? Plus?
yes.
Okay, what's the charge of Q2? Second
Oh,
charge?
it's 2 times 10 to the negative. It's the
Minus
same
10.
thing, just positive.
Okay, so now we have two charges with the what 15 centimeter apart, right? And the problem is the forces on observation point. Where is the observation point located in the problem?
It just says in the middle,
In the middle. So somewhere in this middle of these 2 point position, right? So 20, is that right?
like 7.5. Yeah, like right in the
17.5.
middle.
17.5. No, it's 20, 13.5, right? 27. So yeah,
Yeah.
13.5 centimeters. So now you have distance here, right? So you want to just measure the force between these two. So now the force from that this is positive and this is negative, so that the field itself will be this direction, right? And then you will experience the Coulomb's force at the observation middle of these two charges in this direction. It's obvious, right?
Wait, because it's negative and positive, why can't the negative be attracted to like the positive particle? So it would go to the right as well.
Is there actually third charge in the problem? Is it third charge in the problem, or it just it asks to estimate the force of out of these two charges in the middle of actually two charges?
No, there's no third charge. It's just the two charges.
Okay, then the question asks the amount of the force out of two charges, right? Or force or field?
It says midway between the particles, what is their net electric field in unit vector notation?
Electric field, right?
Yes.
So basically the plus charge produced, now this is just is one-dimensional space. Plus charge produce positive, I mean the electric field outward always. This plus charge. So if you think of force, I mean the field out of this positive charge at the midway of these two, then electric field will be this direction out of this point two, Q2. Okay. And the same electric field, negative charge always inward. So same thing, if you look at the field out of the from this Q1, that's the same direction, this direction. So you just need to add these two vectors together. So they all same direction. So the first one, the field from that is electric field 1 plus electric field 2. So that is K times what is Q1 R1 square, which are, and then this K times Q2 R2 square, right? Here's R1 is what? 13.5 centimeter minus 6 centimeter. That is 7.5. obviously. 0.075 meter. And this one should be same.